You ask an AI a question. In second letters, it pulls the right paragraph from a 200-page document. But the database didn't understand the document like a human. It turned the text into coordinates, organized those documents into a graph, and then navigated that graph to find the closest meaning. We will follow one document and one question through the entire pipeline. Imagine your documentation says, replace compromised credential immediately. A user search, how do I rotate a leaked API key? Those sentences are closely related, but they share very few exact words. A basic keyword search may miss the connection because it compares words and not meaning. This is the semantic gap. People can express the same idea in different words. Traditional databases are still essential. They are excellent at exact values, transactions, joins, and filter. The problem is narrower. Exact matching alone is not enough when a user is searching by meaning. We need a system that can answer these questions quickly. What does this passage mean? Which stored passages mean something similar? Which of those passages is actually allowed and relevant in these contexts? A vector search system solves this with a pipeline. First, split the source into useful chunks. Second, convert each chunk into a embeddings, which is a list of numbers representing patterns in its meanings. Third, store the vector together with the text and metadata. Fourth, build the index that can search those vectors efficiently. Fifth, embed the user questions with the same embedding model. And finally, retrieve the nearest valid matches. Now, let us run the application in this repository instead of conceptual code. For this demonstration, I'm using Microsoft Foundry, where we have deployed a model, text embedding 3 small. It produces 1536 dimensional semantic embeddings, so differently word passages can appear together even if they are using different words. The Foundry endpoint and the API key are already configured in the environment variables. The Docker Compose start 3 services: the FastAPI gateway on port 8000, Qdrant on port 6333, and PostgreSQL. The gateway sends chunk and search queries to Microsoft Foundry endpoint for converting into embeddings. Qdrant stores the vectors and searchable payloads, while PostgreSQL stores relational documents and chunk metadata. Document preparations happens in app chunking.py. This file is a service module, not a standalone command, so we do not launch it separately. The ingestion endpoint calls this as the first stage of the live pipeline. The key strategy here is semantic chunking. Instead of cutting the document every fixed number of characters or tokens, split sentences first preserve natural sentences boundary. Semantic chunker then embed every sentence with a configured Microsoft Foundry model. For each adjacent pair, it calculates cosine distance. A small distance suggests a topic continues, while a large distance suggests a change in the meaning. A chunker collects all of those neighboring distances and chooses their 75th percentile as an adaptive breakpoint threshold. This threshold is relative to the current document rather than being one universal similarity value. It then walks through the sentence in order. When an adjacent distance is greater than the threshold, it closes the current chunk and starts another. Otherwise, it keeps the sentences together. The result is a set of variable length chunks whose boundaries follows the document's strongest semantic transitions while preserving the original sentence order. Let us send the document through call chain. The response tells us how many chunks are created and confirms that one vector was created for every chunk. The exact chunk count depends on text, embedding provider, and configured percentile. Ingestion service now sends all chunks to the configured embedder as one batch. It then creates a point for each chunk. Every point contains a generated ID and a payload with the original text, document ID, chunk index, and the metadata we supplied. Build embedder chooses the provider from configuration. The Microsoft Foundry calls a configured text embedding 3 small deployment. This is the same model that will also be used for creating the embedding for the user query. That guarantees that stored chunks in user queries occupy the same vector space. Because we selected the Qdrant backend, the store creates the document collection with cosine distance and HNSW configuration of m equals 16, ef underscore construction equals 200. It then observes each vector with its payload. The stats endpoint confirms the collection name, vector count, index type, and HNSW construction setting used by this application. The retrieval service embeds this question to the same configured provider and passes the query vector to Qdrant. Qdrant traverses the HNSW index in return the nearest candidates. The API responses exposes each chunk's text, similarity score, and metadata. Now we are at the metadata filter. In app vector underscore store.py, the Qdrant back converts the key value pair into required filter condition. Only points matching every conditions are eligible. The return chunks are not only close to the question that was asked, they also belong to the security department, correct year, and required access level. That is a complete application flow. The ingestion endpoint runs app chunking.py, the embedding layer creates vectors, Qdrant stores and indexes them, and the search endpoint returns the top filtered matches. These are retrieval result, not generated answers. An embedding is a position in a high dimensional space learned from data. We often draw that space in 2 or 3 dimensions, but a real embeddings can have hundreds or thousands. The picture is a projection, not a literal map of every dimension. Similarity is also model dependent. An embedding model optimized for text retrieval may arrange passage differently from one optimized for images, code, or recommendations. With a small collection, a database can compare against each and every vector. That is exact search. But at larger scales, exhaustive comparison becomes expensive. Many vector systems therefore uses approximate nearest neighbor indexes. Approximate is important. They trade a small chance of missing the true nearest result for much lower latency. A common index is HNSW, hierarchical navigable small world. Imagine finding a cafe in the city. You first use highways to reach the right area, then local roads to reach the right blocks. HNSW follow a similar strategy. Its upper graph layers contains fewer nodes and longer range lengths. Move towards promising regions and descend into denser layer for a more precise local search. Important HNSW controls commonly include how many graph connections each node can maintain, ef underscore construction, how much work is spent building a high quality graph, ef underscore search, how many candidates are explored at query time. Higher values can improve recall, but they also increase memory, indexing time, or query latency. Defaults are a starting point, not a guarantee. Tune them against your own corpus and workload. The index still needs a rule for neo. One common rule for text embedding is cosine similarity. It compares the angle between two vectors. A higher cosine similarity means vector points in more similar directions. Vector similarity answers which items are semantically closer. It doesn't answer which tenants own this item. Is it current? Or may this user read it? This is a role of metadata filtering. Depending on the database, filters may be applied before, during, or after approximate match. The implementation details affects both speed and recall, especially when a filter is highly selective. A production retrieval system often adds 4 more layers. Hybrid search combines semantic vectors with keyword signals, which help with exact names, IDs, and rare terms. Re-ranking uses a stronger model to reorder a small candidate set. Evaluations measures recall, ranking quality, latency, and answer groundedness on representatives question. And observability record which chunks were retrieved, filtered, cited, or ignored. The vector database is a fast candidate finder. Good chunking, filters, re-ranking, and evaluation turn it into a reliable retrieval system. So when an AI finds one useful paragraph inside a huge document, here is what actually happened. The document was chunked. Each chunk became an embedding. The vectors and metadata were stored. An index organized the search. The question entered the same embedding space, and the database returned the nearest valid candidates. It is not magic. It is geometry, indexing, and careful retrieval design.